Welcome back to IT 3000, episode 22, and today we're pulling apart one of the quietest but most elegant pieces of every modern operating system, the virtual file system. The idea is deceptively simple. A single read call in your program works whether the bytes come from a spinning disk, a network share halfway across the world, or a file that doesn't physically exist anywhere at all. One interface, every file system, and by the end of this video, you'll see exactly how the kernel pulls that off. So let's pin down what VFS actually is. It's a layer inside the kernel that says, if you want to be a file system around here, you must expose these objects and support these operations. Full stop. Borrow the language of object-oriented programming for a moment, and it clicks. VFS is the interface, the file system driver is the implementation, and the system call on top never learns and never needs to learn which implementation it got handed. So what are those objects? 4 of them, and they cover everything. The superblock represents one mounted file system, its size, its block size, the operations it supports. The inode is a single file in memory, deliberately format independent, built up from whatever the driver reports underneath. The dentry ties one name to one directory entry, and it's cached aggressively. That's what makes walking a path fast the second time. And the file object is one open instance, position, mode, flags. 2 processes opening the same file get 2 separate file objects, but they'll point back to the same inode. Now, who actually implements this interface? Just about everything. Your traditional disk file systems, XT4, XFS, NTFS, APFS, each with completely different on-disk layouts. Network file systems like NFS or SSHFS, where the bytes live on another machine entirely. Memory-only file systems like TMPFs, which vanish on reboot. Pseudo file systems like TROC-PROC and Sys, which store nothing at all. They synthesize their contents on the fly. And Fuse, where the driver isn't even in the kernel. It's a normal user space process. None of them store bytes the same way, yet every one of them answers read identically. The pseudo file systems are the giveaway. When there's no storage whatsoever and the interface still holds, the abstraction is doing real work. Let's make that concrete. Run cat, proc uptime, and it behaves exactly like reading any normal file. Open succeeds, read returns. A plausible-looking string, close succeeds, but nothing is stored anywhere. No disk blocks, no on-disk inode, no bytes sitting at rest. What actually happens is that procf's registered itself against the VFS operations, and when you read, its handler synthesizes that string on the spot from live kernel counters. That's why the file's reported size is 0. There's nothing to measure until someone asks. And that's the payoff. Kernel internals, exposed through tools like cat that were written decades before procfs even existed. Now, to really understand how VFS works, you need to separate 3 objects people constantly smash together. The inode is the file itself, its metadata, its identity, and there's exactly 1 per file, regardless of how it's named or who has it open. The dentry is just a name inside a directory. When 2 dentries point at the same inode, that's a hard link. Nothing more mysterious than that. And the file object is a single open instance carrying its own read position, which is why 2 processes reading the same file never trip over each other's cursor. And once you have that separation clear, a whole family of ideas opens up, every one of them a direct consequence of the VFS design. Everything as a file is only possible because VFS abstracts the operations. Fuse lets you write a file system in user space by plugging into that same interface. procfs exposes kernel state as if it were files. The dentry cache is what keeps path lookups fast, NFS makes the network look local, and namespaces let each process see its own version of the tree. We'll pick these up one by one, starting next episode with the phrase that started it all. So let's leave you with the shape of it. 4 objects, superblock, inode, dentry, file, and every file system driver, whether it's XT4, NFS, or something you write yourself this weekend, implements exactly those. One inode per file, one entry per name, one file object per open. That's why two processes reading the same file keep their own independent positions. And the proof that this really is an interface and not just a thin wrapper over a disk is procread, returns bytes that were never stored anywhere. One interface, every file system. That's VFS. I'm Dargslan. See you in episode 23.